Okay, we are left with the proof of theorem 7.27, and we start by showing the first embedding, meaning that W1P embeds into L infinity continuously, and this is true for every P between 1 and plus infinity. So first of all, without loss of generality, we can suppose that the interval I is equal to the whole real line R. Otherwise, we can just use the extension operator from theorem 7.24. And also notice that the embedding is trivial for p equals to plus infinity, because in that case you have that the W1 infinity norm of u is just equal to u L infinity plus u prime L infinity, and this is clearly greater or equal than u L infinity, and so the embedding here holds with the constant c equals to 1. Okay. So therefore we can assume that p is larger or equal than 1 and strictly less than plus infinity. Okay, to prove the embedding we use a very common trick for this kind of calculations, and the trick is to define this function g of s as absolute value of s to the power of p minus 1 times s. So this is a scalar function, and s belongs to R clearly. So let u in be C1c of R, and we set W to be G of u, so the composition between G composed u. Clearly we have that W belongs to C1c of R, because both functions are C1, and this one is compactly supported. And so this is compactly supported, and in the places where this function u is equal to 0, you also have that g is 0. So maybe let's write it here. So W is compactly since u belongs to C1c of R and g of 0 is equal to 0. Okay. Okay, and the derivative of W is just given by the classical chain rule, and you can compute it to be g prime computed in u times u prime, and if you derive this function you just get p times absolute value of u to the power of p minus 1 times u prime. Okay, therefore for x in R fixed, we have that g of u of x, which is equal to w of x by definition, and here we can just use the fundamental theorem of calculus. So this w of x will be equal to the integral from minus infinity to x of the derivative of w, so w prime of s in ds. And this is true because first of all because of the fundamental theorem of calculus, and then because w is C1 and also compactly supported, so we can choose the value minus infinity here. And now just plug in this calculation inside this integral. We get the integral from minus infinity to x of p times absolute value of u, p minus 1, u prime, integrated with respect to the s. Okay, now notice that, so if you take the absolute value of g here, clearly the absolute value of g of s is just equal to s to the power of p by definition. So we have that g computed in u, absolute value, is equal to u to the power of p. and therefore we can estimate u to the power of p by using this one, by using star. So maybe here let's introduce one extra step. So this is equal to the absolute value of g of u. Okay, and so this by star is less or equal than the integral from minus infinity to x of p times absolute value of u to the power of p minus 1 times absolute value of u prime. And here I'm just bringing the I'm just using this one and bringing the absolute value inside the integral, obviously with a lesser or equal sign. And now since all this function here is positive, the one we are integrating, we can just take the so this will be less or equal than the integral over the whole r. So this is, since integrand is non-negative, okay. And okay, once we get to this point here, we use Hölder inequality. Again, let's write it here. Hölder with exponents p and p prime. So you see I'm using Hölder with exponent p on this one, and I get this term. And instead I'm using Hölder with exponent p prime, which is here, on this term here. So I get p prime times p minus 1, and all to the power of 1 over p prime. And this exponent p, obviously it's a this constant here is just outside of the integral, so we don't care about it. It just stays there. And therefore I get, so let's make a bit more room here. And therefore we get, so now this one is just the LP norm of u prime. And this one is said, so p stays here unchanged. And instead for this one, remember that p prime is defined as p over p minus 1. So p prime times p minus 1 is just equal to p. And also 1 over p prime is equal to p minus 1 over p. So in the end, if you want to write down here, so if you want to write this in terms of the LP norm, because here you have a p exponent, then you have to multiply and divide by p, and instead the external exponent becomes p minus 1. We can do this calculation using this one here. I mean, actually you don't have to do any calculation, because so 1 over p 1 over p prime is equal to p minus 1 over p. So if you want to get this term here becomes integral over r, without this one, u to the power of p 1 over p prime, but this is just equal to integral over r u to the power of p p minus 1 over p, and this bit here is just the u LP norm, and then to the power of p minus 1 because it's here. Okay. Okay, so in the end we deduce that for every x in R, the absolute value of u to the power of p is less or equal than p times these two norms. And therefore, okay, I'm just summarizing this thing here, because I can take the p root of this expression, left hand side and right hand side, and obtain this one. So u of x is less or equal than p to the power of 1 over p times this one, because p minus 1 over p is again 1 over p prime, so you get it here. And here we have to power this to 1 over p. Okay, now you see that things are happening. I mean, here we have an estimate which holds almost everywhere, and so we want to end up with an L infinity estimate in terms of the W1P norm of U. So now the idea is to from this one, the idea is to bound this from above with the W1P norm of U. And to do that, we use this simple algebraic inequality. So this inequality is usually called Young's inequality in the literature, and it's telling you that for every a and b larger or equal than 0, ab is less or equal than a to the power of p over p times plus b to the power of p prime over p prime. And yeah, I should mention that these p and p prime are the same exponents we are considering now, of course. So p is the exponent fixed that we've been using here. So we're assuming that p is larger or equal than 1 and strictly less than plus infinity. And p prime is the Helder conjugate. So okay, now we can apply this one to these scalar values. So a will be u prime LP norm to the power of 1 over p, and b is just u LP norm to the power of 1 over p prime. Sorry, because so clearly they are here. Yeah, so this would be our a, and this instead is b. Okay, so using this estimate here, so from the last one we obtained, by this Young's inequality, we get that this is less or equal than u to LP over p prime plus u prime LP over p. And now, since we are assuming that p is larger or equal than 1, then also p prime is larger or equal than 1, and so we get that we can estimate 1 over p and 1 over p prime. We can just estimate them with 1. So we throw away these two, and we are left with this expression. But this is just the W1P norm of U. Okay, so now if we prove that the absolute value of U of x is less or equal than the quantity on the right hand side. So now and this is true for every x in R. So now let's just take the essential supremum, and so taking the essential supremum, we would obtain that the L infinity norm of U is less or equal than p 1 over p times u W1p. And now, since here we want a universal constant not dependent on p, it's not too easy to too difficult to check that p that for p larger or equal than 1 you have this inequality here. Not this one, but this one. And this is true for every p larger or equal than 1. And so in the end you get 1, or you get this estimate with a universal constant that we call c. It's called c here. So this is the estimate that we obtained in the end. And remember that we proved it for U, C1, and compactly supported. So, but that's usually how things go, because okay, now we proved it for smooth functions, because I mean it was easy to write down this formula. If U was smooth, then this function W was differentiable, right? But now, I mean, now that we obtain this, at the end of the story, we obtain this for all the functions in C1C, and we also know that the C1C functions are dense in W1P, so we can easily pass to the limit in this one by density and extend this estimate to the whole W1P. So indeed, let's do this precisely. So suppose now that U is just W1P of R. By theorem 7.24, the density result we proved earlier, we know that there exists a sequence UN in C1C of R such that un converges to u strongly in W1P, sorry. Okay, so if we apply star star, maybe this is not too clear. So the idea is that we want to apply star star to un minus um. We have, so by applying this one to un minus you get that un minus L infinity norm is less or equal than C times un minus in W1P. And you get this because, I mean, un and are C1C, so you can use this estimate here. Also, because they're still C1, this is still C1, of course, and it's also compactly supported because both un and are compactly supported. So maybe here, let's also mention that this one belongs to C1C of R. So okay, you get this estimate, and clearly here the right hand side goes to 0 as nm go to plus infinity because un is converging, and so in particular it is a Cauchy sequence. Okay. It is a Cauchy sequence in sorry. Okay, since un is convergent in maybe here should have been much more precise. Being un convergent in W1P, I will edit this later to make it nicer, and hence Cauchy with respect to the W1P norm. So okay, since un is convergent, then it is Cauchy with respect to the W1P norm, and therefore this term goes to 0. But now this is telling you that also un minus in L infinity is going to 0, showing that un is a Cauchy sequence in L infinity. Now remember that L infinity is complete by a theorem that we saw. Yeah, we saw this in one proposition. I will reference it later. Now I don't remember the number exactly. And then we conclude, since it is Cauchy, we conclude that there must be a function u in L infinity such that un is converging to u tilde, sorry, function u tilde, strongly in L infinity. But we also know that un is converging to u strongly in W1P. This was our construction here. And therefore we conclude, it's actually immediate to conclude that the limit must be the same. U tilde is equal to u almost everywhere. Okay, now that we know that un is also convergent in L infinity, we can again use the estimate star star on un and obtain that un in L infinity is less or equal than C norm of un in W1P, and this is true for every n in n. And now we can just take the limit as n that goes to plus infinity in this one here, and you obtain the thesis, meaning that un, sorry, not un, and also let's write it in red, less or equal than C u W1P, and this is true for all u belonging to W1P R, proving the thesis. This is exactly what we wanted to prove. Okay, now we pass to the proof of the point A, which is the first compact embedding we stated. So in this case we have to assume I bounded, so this was our interval, or even just an open set. And we need to prove that W1P of I embeds compactly into C of I closed for all P strictly larger than 1 and less or equal than plus infinity. Okay, therefore we just need to show that this operator is compact because because we already know that W1P of I is contained in continuous functions because of theorem 7.19. So remember that every W1P function has a continuous representative, and this just means that W1P is embedding in the continuous functions. Okay, so let's prove that this is compact. So let B be a bounded set in W1P of I. This means that there exists a constant m larger than 0 such that the W1P norm of U is less or equal than m for all U in B. Okay, by the embedding we just proved in the previous point, we know that U L infinity is less or equal than C times U W1P less or equal than Cm for every U in B. Less or equal than Cm because for every U in B this holds. And now, as I was mentioning, recalling that W1P is contained in the continuous functions by this theorem, we get that the U infinity norm, the infinity norm of U, so this is the continuous norm, is actually just equal to the L infinity norm by definition. Just think about it. In the regular case, this is just telling you have to find the best constant, which is bound in the absolute value of U almost everywhere. And obviously, if U is continuous, the best constant is just the infinity norm by definition. So the supremum of absolute value of U. And therefore, from this estimate here, we obtain that U infinity is less or equal than Cm for every U in B. Okay, I mean, the idea here is that we want to employ Ascoli-Herzé law that we stated in the previous class, in the previous hour. And so, as you can see, this estimate is already telling you that that the family U in B is bounded uniformly with respect to the infinity norm, and they're continuous. Now we just need to prove that this family is equicontinuous, and we do that by leveraging theorem 7.23. Because remember that theorem 7.23 was telling you that W1P is contained in C0 1 minus 1 over P, and this is just a space of Hilbert functions with exponent 1 minus 1 over P, and this was true for P strictly larger than 1. And from the same theorem you also get this estimate. I mean, this was in the statement. You get that the absolute value of U of x minus U of y can be bounded by the LP norm of U dot times the difference between x and y to the power of 1 minus 1 over P. And this is true for all points x, y in the closure of I. Now remember that U dot is less or equal than m for all U in B, because we're assuming that this holds. And so in particular, this is larger or equal by definition of U dot LP norm. So by recalling that, then we can use this estimate to conclude that this absolute value here is less or equal than m times the distance between the 2 points. And this will be true uniformly in B. And this shows that, this immediately shows that the family B is equicontinuous. I mean, you can check that, but it's very simple, because equicontinuity was saying that for every epsilon larger than 0, you must find delta such that x minus y less than delta implies U of x minus U of y less than epsilon, but for all U in B. But now it's easy, because if we fix some epsilon and we want this to be this distance here to be less than epsilon, we just take I mean, we know that U of x minus U of y is less or equal than m x minus y 1 minus 1 over P. So we say that this is less than epsilon, and this is less than epsilon if x minus y is less or equal than epsilon over m, to the power of 1 minus 1p to the power of minus 1. I mean, we don't care about the exact exponent. And then you can just take this as delta and proving that this family is equicontinuous. Okay. Okay, therefore, as I was saying, since star and double star hold, so these two conditions, which again tell you, the first one is telling you that the family is equibounded, and the second one is telling you that the family is equicontinuous. Therefore, we can apply Ascoliar-Zerà theorem 7.28 with the compact set given by, I mean, this was the compact metric space. We just take the closure of I. That's why here we are taking the closure, by the way, because we want it to be compact, since it is already bounded. And so if we close it, you get something which is closed and bounded in R, which is compact by the Heine-Borel theorem. And therefore you conclude by the theorem that the closure of B with respect to the uniform norm is compact in C of I of the closure of I. And therefore A is established, because we just proved that if we take a subset of C of I, which is bounded with respect to the W1P norm uniformly, we showed that the closure of this subset B is compact in C of I, which is exactly the definition of compact operator applied to the identity, which was exactly our claim. Okay, let's prove the embedding in point B. So again, we assume that I is bounded, and in this case we assume that Q is larger or equal than 1 and less than plus infinity, and we need to show that W11 of I compactly embeds into LQ. So again, in the previous point we used that for proving that W1P was embedding into the continuous functions in a compact way, we needed a compactness criterion in the continuous functions. Now obviously we need a compactness criterion in LQ, and that's what we're going to do. So to show that this operator is compact, first of all, definition, we need to take a subset B of W11, which is bounded in norm. So U norm of U W11 is less or equal than M for all U in B. So this is our assumption on the set B. And then now let's take the operator P from W11I of W11R, which is the extension operator of lemma 7.25. So by the properties of P, we know that the set P of B is bounded in W11 of R, because remember that P was linear and bounded, so you get that the norm of P of U in W11 of R is less or equal than a constant times the norm of U in W11 of I, and this is obviously, I mean, it is by assumption less or equal than C times M. So also this set here is bounded. Okay. And moreover, always by the property that P of U restricted to I is equal to U, this was one of the properties of the operator B, we also get that P of B restricted to I is equal to B, where we define this capital P of B restricted to I to be the set of all functions from I into R, such that there exists a function in P of B such that V restricted to I is equal to U. I mean, this is just a fancy way to say that we know that this is bounded, and we also know that if we take a function here and we restrict it to I, we get back a function of B by the properties of the extension operator. Okay, now we know that this embedding holds by the first point. So by this embedding, we have that P of B is also bounded in L infinity, because this is a continuous embedding, and we know that P of B is bounded in W11, as I was saying here, and therefore P of B is also bounded in L infinity, since this operator is continuous, linear and continuous. And therefore for an arbitrary u in P of B we have the following. So the q norm of u is equal simply to the q minus 1 norm, q minus 1 absolute value of u times the absolute value of u, and here we can just use I mean, it's not even Hilder inequality, it's just we are taking outside the L infinity norm of this one, and we're left with the L1 norm of u. So we have L1 norm of u times L infinity norm of u to the power of q minus 1, because this is here. And this shows, so this is true for all u belonging to P of B, to be precise. So this is telling you that P of B is also bounded in LQ. Okay, because the Q norm is okay, why is this true? Sorry. This is true because, okay, it's true because this guy here, which was the extension, the extension of U, this is, sorry, it was an element of P of B, so it was an extension. We know that P of B is bounded both in L infinity and in L1, so obviously it is also bounded in LQ. Okay, meaning that there exists a constant m larger than 0, such that the Q norm of U is less or equal than m for every U in P of B. Okay, we now want to check this condition triple star, that the limit as h goes to 0 of the supremum for all functions u in P of B of this translation is going to 0. Okay, and here we use theorem 7.29, which maybe it's a good idea to go back to it. So 7.29 was telling you that if you have a function in LP which is also W1P, then it holds that this guy here, so the translation minus u with respect to the LP norm, can be bounded by the absolute value of h times the LP norm of u prime. So we use exactly this theorem 7.29 now. Where do we use it? Okay, here. So we use theorem 7.29 with p equals to 1, because remember that the implication A implies B holds also for p equals to 1. So maybe let's be precise here. Okay, this can be moved below. So implication they were saying that if A is sorry, that if U is W11, then you get this estimate here, which is telling you that you can bound this term with the norm of U dot, sorry, in L1 times the absolute value of H. And now we also know that, since we know that P of B is bounded in W11, it means that this guy is bounded by some constant. And so you get this estimate here. So this one is less or equal than this one for every u in P of B. And therefore, okay, now we want an estimate for the LQ norm. This was our initial goal. We can estimate this guy here. So this is just equal to this integral. And as usual, we do the same trick as before. The same trick as before is just split this one in these two. So the power of q can be written as the power of this one to q minus 1 times this one. And so for the first one, we just take outside the L infinity norm. So we get the L infinity norm of this guy to the power of q minus 1, and then we're just left with the L1 norm. And yeah, here you can actually check that. I mean, you can actually check, of course, the norm of the translation. If you do a translation in L infinity or in any LP, I mean, this is always equal to the norm of the function itself, right? You're just moving shifting things around on the real line, so the supremum doesn't change. And here I'm saying that tau h of u minus u L infinity, this is by triangular inequality, this is less or equal than tau h u L infinity plus u L infinity, and so this is just equal to 2 u L infinity. And maybe I should write this down here so that we're a bit more precise. So this one was the motivation for this one, and for this one we use that tau h u minus u L infinity is less or equal than twice, let's write down directly the final estimate, twice u L infinity. So this is to justify this inequality. And obviously 2 to the power of q minus 1, because you had a power of q minus 1 in the term here. Okay, so we arrived to this point, and now remember that, so let's delete this one, sorry. We got to this point, and now remember just that by 4, first of all, this one can be bounded by c times h, so which is what we have here, because here we're considering functions u in P of B. And this stays the same, clearly. And we remember that P of B was also bounded in L infinity, so here we can just replace this with a constant c tilde. And so this, oops, sorry. And so this estimate here, this one less or equal than this one, shows triple star, because triple star was this one. Let's see if we can get both of them. Yeah, triple star was this one, and we just proved that this guy can be bounded uniformly in H, uniformly with respect to u. So if we take the supremum over u, the supremum will be less or equal than this term here, so this one here, and this clearly goes to 0 as h goes to 0. And so 3 is established. Okay. Now, since 2 and 3 hold, and I is bounded and q is not plus infinity, we can apply the Fresche-Kolmogorov theorem in 6.17 in the appendix on LP spaces. And so let me take the statement of this theorem, because we never saw it in class. So this is the statement of Fresche-Kolmogorov, which is a strong compactness criterion in LP. So this theorem is telling you that if, I hope, okay, no, let's not do this. So it's telling you that if P is larger or equal than 1, and you have a family in LP over D, then for a measurable set with finite measure, we denote by A restricted to omega, the restriction to omega of all functions in A, which means that these are the functions V from omega into R, such that there exists a U in the family A, such that V is equal to U restricted to omega. And this is very familiar. This is just our set P of B restricted to I in the proof of the compact embedding we were seeing. And assume that A is bounded, meaning that there exists a constant m larger than 0, such that the LP norm of U can be bounded by this constant for every U in A. And also assume that it is equi-integrable. this family, meaning that the supremum for all u in A of this difference, so translation of u minus u in LP, this has to go to 0 uniformly in A, meaning that the whole supremum here has to go to 0 for H that goes to 0. And also this must look familiar, very familiar, because we just showed this for our case, for the proof. Therefore, if 1 and 2 hold, we get that the closure of A restricted to omega in LP of omega is compact with respect to the LP norm, of course. In particular, this means that if un is a sequence in this set, there exists u belonging to the closure and a subsequence such that un k converges to u strongly in LP to u bar. Okay, now we want to apply this to our case, so let's go back to the proof. There you go, we're left with this one. Actually, we proved everything already, because we proved 2 star, which is telling you that for the family P of B, all these functions are bounded by a constant. So the family P of B is uniformly bounded in LQ, and this is telling you that the family P of B is equi-integrable. And these two were just the assumptions of Freshekhol-Mogorov that we just saw. And so we conclude that this family here is compact in LQ. I mean, the closure of P of Bi is compact in LQ. Now, recalling that P of Bi is equal, P of B restricted to I is equal to B by construction, we have that the closure of B is compact in LQ of I, which shows the thesis. Now, very quickly, we address C. And as I was mentioning earlier, this is just a consequence of the previous points, because for so in this one we had to prove that this embedding here is always compact if I is bounded, of course. Compact. Now you see that for P equals to 1, this becomes the embedding, this embedding here, which we just showed in point C. In point B, sorry, which is actually a special case for Q equals to 1. So this is with Q equals to 1. And instead, for P between 1 and plus infinity, with 1 excluded, the embedding that we want to show, this one, compactly of course, follows from the compact embedding that we showed in point A, and from the fact that, so if you take a subset here which is bounded, this embedding is telling you that the closure of this subset is compact in these functions here. And now you can just check immediately then the uniform convergence implies LP convergence on bounded intervals, so meaning that if you take a compact set here, it will be also compact in LP. And so you get that this embedding here is compact. Okay, so this closes the proof of this theorem. Okay, in the few minutes we have left, we look at one remark covering the cases we didn't see in the Sobolev embedding theorem we just proved, and also a corollary of the Sobolev embedding theorem. So first remark is that, okay, we proved that W1P embeds compactly in the continuous functions for every P strictly larger than 1. The question is, what happens when P is equal to 1? So of course we know that this embedding is true because of the usual theorem that Sobolev functions are continuous. However, the fact is that this embedding is in general not compact. So for P equals to 1, compactness fails in this one. The second remark is that, okay, we know that compactness fails for P equals to 1, but can we say something at least? And yes, and this is called Helly's selection theorem. which tells you that if you have something bounded, so a bounded sequence in W11, then there exists a subsequence such that U and K converges pointwise for all x in Y. Y closed, I suppose. And so this is just telling you that you don't have uniform convergence like you do in this case here, because this embedding was compact with respect to the L infinity norm of uniform convergence on the continuous functions. But instead you only have pointwise convergence. Okay, so these are second remark. The third one is that if I is unbounded, we know that W1P embeds into L infinity for all P strictly larger than 1 and less or equal than plus infinity, and this was proved in this was the first statement of our theorem. However, this embedding is never compact. This is important to know. You never have compactness, so you cannot expect uniform convergence in any case for bounded sequences here. Okay. The third remark is that okay, if I is unbounded, what can we say? So of course here, sorry, I paused for a moment because I thought that this was contradicting what I was saying here. I mean, was contradicting this embedding, but actually here notice that we're saying that I is unbounded, whereas this embedding holds for I bounded, which makes a huge difference. Okay, so the first remark is that if we assume that I is unbounded and P is strictly larger than 1, then if you take a bounded sequence here, there exists another sequence. Sorry, there exists U in W1P of I and a subsequence such that you have strong convergence in L infinity of J for every J in I bounded. So okay, this is the negative news. So the bad news is that if I is unbounded, this is not compactly embedding into L infinity, but instead what's happening is that it is basically compactly embedding into L infinity of J for any interval J contained in I which is bounded. So J has to be bounded. And instead, if I is unbounded, then we know that W1P of it is true that W1P of I embeds into LQ of I for all Q larger than P. However, in general, it is not true that this embeds into LQ of I if Q is between 1 and P. And this was exactly, I mean, the embedding we had in C here. Yeah, this was for W11 embedding into LQ. And here I'm saying it in general for W1P. And we didn't prove this, but just know that this is true. Although we will probably never use it in this course. Okay, a corollary of the theorem is the following. So this is just a corollary of point C, so of the embedding W1P compact in LP for I bounded. So let I equals to AB be a bounded interval and P larger or equal than 1 and less than plus infinity. Assume that UN is converging to U weakly in W1P, meaning that UN converges weakly to U and UN dot converges weakly to U dot. So this is the definition of weak convergence in W1P. Then from this we deduce that actually this convergence is strong, so that UN converges to U strongly in LP. Okay, so this is telling you that the weak convergence in W1P is equivalent to asking strong convergence of the functions and weak convergence of the derivative. And to prove this one is immediate, because this is just from point C of theorem 7.27. We know that this embedding is compact, actually for every P larger or equal than 1 and less or equal than plus infinity. And yeah, why didn't I put plus infinity here? I didn't put plus infinity here because the weak convergence in L infinity is not a weak convergence, so we don't talk about it. Okay, it's called weak star convergence, but for the scope of this course it's not interesting. So okay, we have this compact embedding, and then the thesis follows by applying the remark on compact operators at the beginning of this section. So I was saying at the beginning that a compact operator sends weakly convergent sequences into strongly convergent sequences. And so since this is compact, this is telling you that if you take something which is weakly convergent here, then it is strongly convergent here. Oh, and of course this argument applies to all the other embeddings that the compact embeddings at least, that we proved. So for example, for this embedding, if you take a sequence which is converging weakly here, then it's also converging uniformly. Always for the properties of compact operators. And same here. Weak convergence in W11 implies strong convergence in LQ. And this is the one of the corollary. So weak convergence in W1P implies strong convergence in LP. Okay, I think that our time is over, and next time we will resume with subole spaces. We will look at higher dimension subole spaces, and also about how to treat boundary conditions in subole spaces and the Poincare inequality. And then from there we move back to the calculus of variations, and we end this parenthesis on subole spaces. So okay, see you next week.